Nice. Not this. Nope. I think it's this one or this one. Yeah, it's this one. So as you guys remember, the first week we did this, like last week we spoke a little bit about segmentation. We have already been through this lab, like we have already like read all about this lab before in the, I think 3 weeks ago or something. But it's worth it to go back through it, because last time we presented it as just a bounding box regressor, or basically an object detector. But now we're going to see it as a what is it called? As an instance segmenter, right? So it's an instance segmentation technique. It's called mask RCNN. We've already seen it during the lecture, but it's now just worth looking back at the lab and seeing what makes it special, right? What is the difference between a typical object detection technique and a segmentation or instance segmentation technique? And hopefully you guys will be able to build your own instance segmentation technique for the homework. So the next homework is going to be a simple instance segmenter, very similar to the first homework, where you will basically create your own data set. But now you're not going to be using just a basic bounding box data set. You're going to be creating a segmentation data set. It's a little bit more work. It might take you a little bit more time, but since you guys already have the data, you already have like the classes set up, and it's just 100 objects at maximum. So I guess it's gonna take you like, I don't know, 15 minutes to annotate the whole data set. It will be a very good exercise for you to just make all of these labels by hand. And then what's gonna be interesting is to see how you guys read your data set, right? So reading the data set now becomes one of the hardest, let's say, parts of the training of the model, because for the majority of your models that we have seen before, like the YOLO and or the versions of YOLO, they use a specific format of data, right? So they use a format that is a bit, how do you say, like textual, and you will have simply something like this: X center, Y center, and then width and height. And usually you will have here like the class index. There are multiple variations of this. So it could be something like this. If it's not X center, but X top left, and Y top left, and width and height. And it could be the last version would be these numbers normalized based on the size of the image. So it's going to be the same exact two numbers, but they will be just normalized, right? So these were the formats that you have in basic object detection. And the good thing about these is that they are all very well known and they are very simple to work with. But the problem with instance segmentation is that it becomes more difficult or more challenging to do so, right? This representation is very easy because you're trying to represent a rectangle. There are only so many ways that you could represent a rectangle, right? And all of them are being used or have been proposed as a method to like save your data, save the annotations of your data set, either in a YAML file, or either on a JSON, or in, as we said, just a basic text file. But then the problem when you're working with instance segmentation especially is that the segmentation now becomes more challenging as a data structure that you should be keeping, right? So here you will need to basically write your own code that converts the points that you manually build for the image. So the contours of the objects, you will build it manually, and then you will have to convert those numbers into a format that the model can understand. So this model is pretty simple. So this is the model that we said, it's mask RCNN. It's pretty basic to use, but it might require a little bit more like hand work to get this done. Also for your, what is it called? For your homework, you're going to be using, again, YOLO V8, as YOLO V8 is not also only a, what is it called? An object detector, but it's also able to perform segmentation. So for that task, the names of the, what are they called? The names of the architectures are usually YOLO V8, and then followed by the size, you know, N, small, medium, large, or extra large, and then just like a column segmentation. That's usually like the main difference that you will be doing. That's the only thing that you will have to change from your previous code to your new code. The majority of your work is going to be mainly on building, annotating this your own data set, the same data set that you use for homework 1, and then for writing the code to read basically that data set into a mask RCNN format. But the YOLO VN format is going to be quite easy to convert to. So it's going to be very easy, an easy task. All good?
Yes.
Nice. So for the next week, as we said, you're going to have like your mid evaluation for the project. Plus, you're going to have the, as we were just saying right now, the second homework submission. So I'm going to open the submissions for the next, for the second homework today, and you will have like 15 days to work on that and hopefully give back the project. The project is going to be, or the homework is going to be exactly the same version or the same style as the first homework. So you're going to have to submit a GitHub repo. The GitHub repo should contain a README that contains lots of images on how you did the modeling and lots of evaluations of the models. And then, of course, you will have the code of the training and of the maybe data conversions that you used. Preferably also a link to Colab so that I can just easily and quickly run the data set and make sure that it works. So now that is all that is said, let's go to the lab really quickly, execute it, and see how the actual data is being used. Oh, that's cool. Now they changed it. Let's go and change the code for this one. Colab. What is it called? Bittechatron. Nope, not this. Colab number. Should be the good one. Does it expect PyTorch version 2? Okay, it does not. Yeah, so the problem is now that we have PyTorch version 2, Colab by default goes to that version. So let me just make sure that all is good. Although it's backward compatible, so even if it's not there, it should be quite quick to install. Let's see. Okay, seems nice. Let's go here. What is the Torch version? Can somebody see it? So Torch is, wow, 1.13. Did we install? Okay, that's weird. I expected PyTorch to be the latest version, but it's not. let's do the imports. I hope they did not delete the data set though. Okay, all good. They did not delete the data set. Nice. So now I'm just gonna put a simple break in here and look at how the data looks, right? So the data is located in this balloon data. Let's go to the validation. It's usually smaller. These are just images. Typical, right? You expect this. Not a big surprise. Now, when we go to the validation data, you will see this kind of file. Let me just take this and put it into something that is more readable, right? Open. Let's go PyCharm, new project. Okay. I think there is something called like JSON beautifier online. Yep. Yeah, there we go. So you will have like a big JSON. This is how your data is going to be organized, right? So a big JSON file that contains the following, right? Each image will have its own dictionary. Makes sense. Let me also do it from this side. File data.json. Nice. And then inside each one of these files, you will find the name of the file, the size of the image. No file attributes here. There's just like the metadata. And then inside you will have this regions dictionary. You go inside it. Let's just close it up a little bit. Region attributes. These are some metadata that you could be using. Shape attributes. So inside the shape attributes, you will have the type of object that you're using, or the type of object that you're trying to classify. In this case, we're aiming for a polygon shape, which is the shape used for segmentation. If you're using the JSON like this JSON data structure to keep your object detection, object detection data, instead of polygon, you're going to have something like rectangle, right? This name is exactly the name that you will be finding on RoboFlow. So if you go to RoboFlow, and I just take any data set like this, and then annotate. Let's see. Let's annotate this one, for example. Here you can either do a bounding box tool, or if you can see here, a polygon tool. So the polygon tool just allows you to do this, right? Multiple points. Up and done. So this is our polygon. As you can see, it's quite fast. Last thing you have to do is choose the class of this object, and you're good, right? This right now is not correct, so I'm going to take it off. So the task itself is quite simple. As I said, in terms of annotation, you just go to the image, do the annotation quickly, and you should get here by default everything that you need. So name is polygon. And then the second point, or the second part of this shape attributes, is the all points X and all points Y. So what you will see is that it is split into two arrays. The first array gives you the X coordinates of all the points that you just built. So if we go back here, let's do some I don't know, let's annotate this one, for example. All points X will follow the X coordinates of all of these, what are they called? Of all of these contour points And the most important thing is that they will be followed in order. So please do not like mess around with the order of these points. All points y will have the y coordinates of the exact same points in order also. So this is point number 1, has 916 of x and 515 in y. And in the code, in your code, you will have to basically read exactly what we just said. So you will have to read the JSON, get the file name, and create this kind of dictionary, big dictionary of annotations that you will be feeding into your model. The dictionary must contain for each image the file name, a random index if you want, or just like an index based on like when are you reading it, but just a very unique identifier that will be used later on for loading the data. Height and width, this is some information that in some data sets you will find exactly in the JSON, so you don't have to basically read the image to do that. But in case you don't have this information, then you will have to manually read each individual image and then calculate its height and width. This is, again, as I said, only for the cases where you don't have the information about height and width. But in the majority of like the model that, or maybe in RoboFlow, you will find already in this file attributes, you will find information about height and width. So if it's already there, preferably use it. Don't have to read every single image because this takes a lot of time and makes your code a lot slower. If you just read it directly, it's quite fast. So then what you do is you go to annotations, regions. Inside these regions, you assert that it is region attributes. You go into basically the shape attributes. Let's go back here again. So as we go, what we said is you go to regions, you assert there is something here, and then you go to shape attributes. And here what you will be seeing is the code that basically converts the points from this format into first a bounding box, which is quite simple. So you have the y's and the x's and the y's. If you're going to be building a rectangle or a bounding box model, what you will have to do is give it the top left corner, meaning this point, and the bottom right corner, which is this point. And these points are the minimum in terms of x. So imagine you have the object like this. This is our object. Yeah, this is our object. The smallest x possible inside these contours will be the x used for this border, and the smallest y will also be the x used for that border. The maximum x and maximum y will be used for this point. So this is easy. Again, depending on what format, as we said, of object detection you will be using, you will have to specify a different type of B-box mode. So as we said, you could go with XY, XY absolute, XY, XY relative, X center, Y center with height absolute, X center, Y center with height relative. So there are 4 formats that you could use. Depending on whichever you want to use, just change the box mode and it will figure it out by default. And later we go to the how do we convert into the polygon or the segmentation part. In the segmentation part, what do we expect is an array that contains the following. So P for X in poly for P in X. So X, where is X? Yeah, so X in polygon, here's polygon. So it's X plus 0.5, Y plus 0.5. So what we're doing is we're merging basically the X and Y coordinates in the same tuple. And then what we do is we convert all of those into this format. Let me stop annotating like this. And what we will do is we will print all of these different transformations and see how they look like. So first, let's print px and then print py. Let's look at them as how they become in here. So let me just say tuples of contours and then print poly. And the final version would be print ready for segmentation. And this looks good. Print poly, all good. Let's run. I'm not going to register it again, but I will be calling it. And then we do this. Let's just use the validation data because it's going to be much smaller. And I will close this one. Let's go. So these are all the examples that we got. Let's go up to the first one, for example. Sorry. Here it is. So these are the coordinates that we find for the image. We could print also the image file name or the, let's go, print here. File name. And I will exit. Nice. It did not exit. It crashed. Let's say, let's just throw an error instead. Already downloaded. Oh, I have to restart everything. It's gonna take some time. How did this happen? Didn't we just install it here? Then we go runtime, change runtime to GPU accelerated. Let's terminate them. And let's see how fast this goes. Then run again. Okay. Does everybody at least like know how to do like the segmentation and everything is all is well? And when it comes to this one, let me just delete this so that we don't destroy the data. Delete. Yep. So is it clear now how to do all of these things? If you want to do like the attributes, put some comments, add some tags. Later on, we will see how to use these tags for if you would like to do some domain adaptation or something similar. So all good is here. All is well. I hope. Yes, this is expected. So now we're looking at this file. So this is the image that we are looking at, and these are its PX. This is its PYs. These are how the contours would look like. So the contours would look something like this: 916.5, 515, 931, 913, 583. This 0.5 is just here to make sure that we don't get too close to a number that is 0, and that might lead to like some bad problems later on during the training. So it's just here to make sure that we don't have some bad values in this location. And then how do we convert this into basically a ready for segmentation? As you can see, it just converts all of this into a string where you have px1, py1, px2, py2, px3, py3, and so on and so forth. And this is how you should represent your polygon for the segmentation. So how does it come? It comes as all points x, all points y. And how do you expect it in your code? It is expected as x coordinate, y coordinate, x coordinate, y coordinate, and in this exact same order. And this is how the code would understand the segmentation and hopefully would give you your segmentation. So enough of these. Let's not print the individual numbers and repeat it again. Final time. Let's keep the file name and let's take this. Let's print the record. Let's go. Let's take any one of these records, right? Nope. Where's the file name? I'm still printing the file name, right? Yep. Let's do this. Okay, easy. So file name, and then you get a dictionary that contains a file name. Image ID is a random number that you are generating. The height and width are being read from the image itself. And then you have this annotations, the bbox, the bbox mode, and then the segmentation array that we have just seen. And then finally, you have the category ID. For my case in here, I have just one category. So all the boxes would be, or all the objects will have the category ID 0. But for your case, you will have multiple objects. So please just remember to change this line into whatever category ID you chose. Just make sure that, for example, you do something like this. Classes equals whatever classes you have, right? You have just multiple classes in here. And then the category ID must be exactly the ID in this classes table. The classes table, as we have seen previously, you will be sending it here in the metadata catalog, and you just set what are the classes for your data set. And once this is done, the rest is exactly the same as you have seen for object detection. So here you're checking that you read the data correctly. As you can see, we are reading the data correctly. Everything here is being initialized correctly. All good. Very good example, by the way. So if you have something that is overlapping over the object, always remember to only contour the parts of the object that are visible, okay? And then here you will start doing the training. Remember, you're using mask RCNN instead of faster RCNN as you did in your previous lab. So just setting this into the architecture that you need, mask RCNN should give you the good results that you are expecting. Afterwards, just validate basically your mask RCNN model. Let's come here, present these numbers. You're already now familiar with what does AP mean, AP50, FP75, and AP small, AP max, APL. All of these average precision numbers could be used. So depending on your class or depending on your, on the type of object that you're using, it depends on this. So here, for example, average precision from ranging or getting the intersection over union from 0.50 to 0.95. This is the average precision that majority of people would be using. This is the default average precision that you should be reporting. But in some cases, so for example, if you want to go like a little bit more relaxed, just go with AP50. If you want to go a little bit more severe, just go with AP75. And if you want to have like a small, medium, and large, basically, what are they called? APs, average precisions, then you just go with the APM, AP small, and AP large. It depends on your exact data set. Some of you guys have used objects which are extremely large, so this is what you should care about. But if you are taking the pictures like a bit zoomed out, right? So you're looking at the object from afar, then the most important metric that you should be looking at is the AP small. This is going to determine how good your model is or how good it's not, right? Just remember that these are the models, or these are the These are the results for the object detection. And these are the results for segmentation, right? And usually you see, well, usually actually it's the inverse. Usually the object detection is a bit better than the segmentation, but in this case, it's a very small data set and it's pretty simple task. So the segmentation was actually quite nice for a segmentation task. This is it for the part of segmentation. I think it's a pretty clear one, especially if you have already done your homework. So you already know what I was like presenting in these locations. And I hope that the second homework would be a little bit better. So the majority of you got a really good grade in the first homework. So I hope the second homework is going to also bump up your grade in the same manner. Again, you will be training both versions, so MaxCar CNN and YOLO V8. And I think that's it for the lab part for today. Do you guys have any questions, or should we just go to the lecture?
I have a little question.
Yes.
Could you go back to the code? Like, I didn't get like when we signing the object, like we have B-box there and B-box mode, something like that.
Yes.
Yeah, like
what is B-box?
Yes, something like that.
Yes, let me check all the B-box modes first. Once you have all of them, you will understand what these numbers are. So B-box mode, let's come here. Here it is. It's an enum. How do you get? Let's check. Python get values in enum from enum class. I think it's, yeah, for e.value. Let's go. And we're going to do it on box mode. Here's box mode. Is there another? Okay, let's do this dot list. Yeah, box mode dot list. Let's see. It does not have it. Let's try to access the code. It should give me the ability to access the code. If not, then we just go online and check it out. Okay, here we go. Yes, we got 4 or 5 different ways. The first one is XY absolute. So this is the absolute value of the coordinates. This X0, Y0, it refers to this point. So this is your bounding box. You can represent your rectangle in different ways. The first way, this is X0, Y0. This is X0, Y0, X1, Y1. So by providing these 2 coordinates, you're able to represent basically your rectangle. Another way to do this is to provide XY width and height. And this means you are providing this. X, Y, and then the width and the height, right? So from the width and the height, you can easily deduce this point, right? So these are just different ways that you could represent the coordinates of your model. And here you can see, instead of absolute, you will have relative. So basically it is relative to the size of the image. So instead of being like an absolute point, saying like 0.200, you would have something like 0.3. So this is relative to the size of the image. Also the same thing for XY, WH relative is going to be, relative to this one, to the size of the image. And then the final version is XY with height absolute. No, this is XY. What is the A? It stands for and angle. Okay, so this is the angle, right? So the X center, Y center, width, height, and then the angle. In absolute floating points, coordinates, X center, Y center is the center of the rotated box, and the angle is the degrees in CCW. So if you have a box like this, you can still represent it for this case. Does that make sense?
Yes. More question. Like, is it like, so this is will depend on how we annotate our object in RoboFlow or not? For example, instead of box, we annotate our object in RoboFlow using like polygon.
Both. No, it's gonna be in both, right? So even if you do just the polygon, so let's go to RoboFlow real quick. So you see, even if I did, let me just annotate, remove this. let me just do the polygon. This is the polygon for it, right? I'll do it really quickly. And automatically, save. Automatically, it's gonna generate its own box. So when I download it later, it's as if I did this. Later on, it's gonna generate a box around this. So the bounding box is extremely required. Can you tell me why the bounding box is extremely required? This goes back to the architecture of mask RCNN. Why do you think the bounding box is still required for a segmentation task? You see, we annotated only the segmentation, and by default, it generates this bounding box. It's not by default, so basically it's us who will mention it here. But why do we need it? Why do we have to build this representation? This is the code of the architecture. If you want to go down to the architecture and tell me why exactly in this architecture we will need the bounding box. It's here. Anybody has an idea? Very simply because the mask RCNN architecture is just a copy paste of the faster RCNN, or the faster RCNN architecture, right? And faster RCNN architecture is just fast RCNN plus RPM. So what ends up happening is you are truly training an instance segmenter, right? But in order to train your instance segmenter, you must train first a faster RCNN model that predicts the location of the object. And then you simply train a basic, what is it called? A basic model that does the, how do I say this? The segmentation of that box. So what ends up happening in your segmentation is you will first detect the box, and then you will segment what is inside the box. This is why you must always, for whatever segmentation model you're going to train, you must always provide it with the bounding box and how, of course, you will provide the bounding box. So this information is extremely important because the segmentation part is like the final and easiest part that you will be doing. The most important part is, again, don't forget, you will always be training a what is it called? A fast RCNN architecture, meaning you will be training a object detector on it. So instance segmentation, just like a very quick, let's call it a formula. Instance segmentation is equal to bounding box detection plus semantic segmentation. And we already know what semantic segmentation is. Semantic segmentation is just basically a decoder from last lecture where we spoke about autoencoders and what are decoders, right? And here, if you look at the architecture itself, this is the architecture of the mask RCNN convolution. The name already says everything. Convolutional upsampling head. So this is exactly what it does. It's just a basic convolution followed by an upsampling followed by a convolutional layer. That's all it does. It's a very simple architecture. It takes your bounding box and it tries to basically map it back into a real mask. If you want to check how the mask looks like, let me give you how the mask looks like, right? Here is how the mask that you will be predicting using the mask RCNN look like. It's just a very big array. As you can see, it's three-dimensional array. You have an array for each class. And in here, what you will have is the following. Any object or any pixel that does not belong to the object, it's going to have the false, so 0. And any point that belongs to the object is going to have a 1. As you can see, the majority of the pixels outside are set to false, but there are some pixels that will be set to 1. Let me just check that out. Predicted class, not the predicted class, predicted masks, right? Dot, and you could just check if there is anything that is set to true by setting .any. And it is true. If you want to see how many pixels are set to true, you will see that we have 68,408 points or pixels that belong to the object. If you want to know what is the size of the object, just basically take, how do we do this? Dot, let's make sure it's in the CPU, dot numpy. It might throw an error later on, dot sqrt. Not sure if this works. Yeah, it doesn't have sqrt, so let's just go with sqrt on top of it. Not sure if this is a function, so let's just use numpy.sqrt. And this is basically the size of your object is 261 pixels by 261 pixels, right? It's not that big, right? 261 pixels is just barely visible even. All good?
Yeah, clear. Thank you.
Nice. And here you will see total loss, classification loss for the classifier part of the fast RCNN. Bounding box regressor, that's the first, the regression part of the bounding box detection or the object detection. And then you have the mask loss, which is the loss that you will be training for the mask RCNN, which is basically your segmentation loss. And here you can follow all of them, how they go down, right? So here you go from, the total loss goes from 1 point, or let's say 2 to 0.3. And the classification loss is very accurate, mainly because you have just one class, so it's easy. And where the regression loss also goes down like 5 times. It goes up a little bit at the start, but then it goes down very quickly to a good number. And here we see that the mask loss is much better than these two. And this is why you have very good, what is it called? When we go to the evaluation, for example, we saw that, yeah, the average precision for, what is it called? For segmentation is better, just a little bit better than the average precision for the object detection. And this is very nice because especially for the cases where you don't have enough data, then it's very helpful to give the model more information about the objects, right? So in this case, true, a bounding box is good information to help the model understand where the object is, but segmentation gives the model a lot more information to understand where the contours of the object are, and that should help the model really understand what you are looking for, right? So segmentation should help you train even a better object detector, right? Training an object detector on its own and training an object detector with segmentation will give you a better object detector than the one that is trained without the segmentation. So in case you don't have enough data, segmentation is also a way that helps your model become better at generalization. All good?
Yes.
Nice. So let's take a 5 minutes break and we go back and we try to go through a lecture. So this lecture is going to be very quick. It's a very simple lecture. It's gonna contain some parts about last week's lecture, which was, autoencoders, variational autoencoders. And then we go to something called pixel RCNN, which is just basically a model that generalizes images based on RCNNs. I thought this would be like a good transition from, the computer vision world into the world of, what are they called? Into the world of, help me, into the world of natural language processing. So you will see what RNNs are inside images. And then when you go to hopefully when you go to the natural language processing, RNNs are going to be much easier to, to generalize to. And then from there, we will just speak about GANs and what GANs are and how you can train them. If we have enough time, we will discuss a little bit, as we said, on diffusion models. But diffusion models are very simple concepts. So if you understand autoencoders, you understand pixel RCNNs, and then you understand GANs, then you should really not suffer at all when you are looking at diffusion models. So let's come back at, what time is it in Russia right now?
10.
Yeah, so let's come back at 10:07.
Okay.
Okay, see you soon. Recording. Yeah, so now let's go just really quickly over the following concepts. So we will just see what generative models are in general. Then we'll speak about pixel CNN and pixel RNNs. And then hopefully we quickly go through autoencoders because we have already seen them yesterday. And I'm sure that you will have them again in some future courses about computer vision, or that's at least what the education department has told me. And from there, we start speaking about GANs in general, and hopefully their application to concepts like domain adaptation, right? I'm not going to go too much into the math because I think you already did the math in the machine learning course, or if not, then you will be doing it in the machine learning course soon. So let's get straight into the concepts that we will be covering. So this will be a pretty interesting part because this will be very heavily inside your final exam. So just if you're not watching it right now, then definitely it's worth watching later on, right? So let's start the lecture. These slides are just the slides from the University of British Columbia, mainly because I really like the slides, and these are like the slides I use to actually learn the topics. So it's pretty simple. They're available online. I will give you access to them on Moodle, and they're quite direct, very well explained. There's a lot of text in here, so even if you don't look at the recording, you can easily understand what is happening in here. So let's go with the lecture. So first they start with saying what is supervised versus unsupervised learning. So supervised learning, you basically take the X, which is the data, Y, which is the label, and the goal is to learn a function or a map that takes X and gives you a Y, right? So the examples are classification, regression, object detection, semantic segmentation, image captioning, and more. Here's for example, object detection. You're already familiar with this one. Supervised learning, this is semantic segmentation. Instance segmentation, or also familiar with this one. Image captioning, here it is. Unsupervised learning, on the other hand, the goal is you take some data and you don't have any labels. So the goal is whatever you want it to be, right? So learn some underlying hidden structure of the data. So for example, if you're doing k-means clustering, which is something that you have already done in the machine learning course, the goal is to understand what are the basic components or the major components of the data, how the data is splitted into different categories. You can use that to understand maybe the segments of your clients. If you are, I don't know, if you're a big company, you're trying to segment your clients into like teenagers and adults and stuff like that based on their purchasing behavior. So this is something that you could do with k-means clustering. And there are other techniques also that fall under the unsupervised learning umbrella, like clustering, dimensionality reduction, and this is a very important subject, dimensionality reduction using TSNE. This is something that I highly recommend that you guys do. I'm not going to go through this in this course, but if you are going to be working in like the research field of like computer vision or any field of, any field that takes basically research in deep learning, then dimensionality reduction and especially TSNE are very important concepts that you guys have to learn. I'm sure that Professor Khan has given you PCA, right? PCA is also a form of dimensionality reduction, but TSNE is like way superior and it gives much better results. And then of course we have things like feature learning, density estimation, and etc. Here's dimensionality reduction. And now let's go into the final part, which is generative models. So generative models are a form of unsupervised learning They can be a form of supervised models, of supervised learning, but for now, we're taking them as a form of unsupervised learning, right? So they are generative models that are unsupervised, completely unsupervised models. And the goal is, given some training data, you must be able to generate samples from the same distribution. To simplify this one, you're given a simple data set, you want to generate images that are similar to this data set, but they're not the same, right? So you're not just copy pasting or, just, how do we say this? You're not just learning the exact data, but you're generating something that is similar from the data set. Different people will define this concept differently. So some people will say, we want you to generate or to sample from the same distribution of the data. Others will define it as generating images that look similar or that are indistinguishable from the training data. There are different ways to define basically the goal of a generative model. And in each one of these ways that you define what the generative model is, you will have a different approach to model them, right? So we want to learn a P model X of data that is similar to the probability distribution of the data itself. Now, it's important to note that these data are images. So the concept of P data of X, or the probability distribution of a group of images, is still a very, very not well explored concept in mathematics or in the field of at least computer vision, right? So this is not something that we know how to represent. This is not something that we can easily manipulate or work with. This is why many, many techniques exist that kind of estimate this P of data in a different way, right? Some people estimate it as a conversion from, from a random sample into an image. And this is what GANs do. Other people estimate it as, we'll see this in the following steps, don't worry. So the goal is to basically learn, as we said, a P model that is similar to the P data. P model is something that we can interact with and we can use, whereas P data is just something that we can see, but we cannot really touch. It's not like a tangible concept, right? It's not something that we can calculate or even touch. And this will lead to so many problems ahead, but we just basically ignore it. That's the solution for now. So the goal is to address the density estimation of this problem, and the core problem which is a core problem in unsupervised learning. Explicitly, density estimations basically would explicitly define and solve for P model of X, whereas implicitly, it will try to learn a model that can sample from the P model of X without explicitly defining it. So as we said, there are two types of models. The first one, which is this one that basically defines P model of X. And the second model is just the implicit way of working with this. And this one is what we see usually in GANs. We will go to the second part, hopefully really quickly. But for the first part, this is what we are mostly interested in, right? So for today's goal, we will see that there are multiple types of generative models, as we said, explicit density estimators and implicit density estimators. From the side of implicit density estimators, we will be speaking about GANs, in like 15 minutes. And for the side of explicit density estimations, there are different techniques, but the most important ones are tractable density, such as pixel RNN and pixel CNN, and then the approximate density using things like variational autoencoders. I'm not going to go too much into detail about variational autoencoders and approximate density estimators, but we have already seen them, I think, last time. If you would like to understand the math behind it, you will find it in the last slides of this lecture. But if I'm not mistaken, and I have taken exactly the same courses as you did, you have already done that part, or you will be doing it really soon in another course. So I'm sure there will be a course that explains very clearly what the math behind variational autoencoders is, or the KL divergence and all of these concepts. So why do we use generative models in general, right? So for now, the goal is to basically generate these samples of artworks, super resolutions, colorizations. It can help you go from ideas to an actual project really quickly. We have seen things like, what are they called? Mid-Journey, generating images that are not just extremely realistic, but like crazy realistic. It's quite fun for now, but soon it will have like extremely lucrative applications. So things, for example, you just upload your picture and it will put clothes on your picture from like a certain catalog, right? So you go to Zara or you go to H&M, you just upload your picture and now you can see yourself in their clothes. You don't have to just go to the shop and, you know, test the clothes and wear them to see if they look good on you. From your home, you can test it, see if you like it, and buy it really quickly. So there's very big potential in, you know, in many industries to use these generative models, right? So especially for images. So generative models of time series data can be used for simulation predictions, planning, reinforcement learning applications. So things like generating hyper-realistic game scenarios. For example, I don't know, you're playing GTA and well, the map, just like, imagine like a map that is impossible to finish, right? It's just a gigantic map. Anywhere you go, it is creating the world as you go, right? So while you're walking through the world, it is generating your new map and you're just creating new potential. And that would give you access to like games, for example, a game that only you are playing, right? So you're playing a game that no one else in the world is seeing, or a part of the map that nobody else has access to. Training also generative models can enable inference of latent representation that can be useful as general features, which we have seen in the case for example, autoencoders in general or variational autoencoders. They learn this latent space, the Z, that could be extremely useful for things like classification, right? So you take the encoder, add a classifier on top of it, and there you go. You could have a good classifier in the case of a classification task that is low on images, right? Or low on labels. And then, of course, streaming or hypothesis visualization. The two most famous architectures in the first part of generative learning or explicit generative learning are Pixel RNN and Pixel CNNs. So starting with the Pixel RNN, it's a very simple idea, right? What it says is you will try to generate the image as if it was a sequence, right? So what you will be doing is you will generate the first pixel in the image, and then you will generate the next pixel, 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 and so on and so forth, and so on and so forth, until you generate the whole image, right? So it treats the image as just a sequence of pixels that you will have to generate, which is a very simple thing. It's pretty slow because you will have to repeat it thousands and thousands and thousands of times, but theoretically, it's quite simple. You just take one pixel and you generate the next. So it's a very simple thought strategy, right? So it's a very simple model to think about. It's definitely worth trying. It doesn't give good results, but it is worth trying, right? So what we're going to do is explicitly model or represent the density function of the data by saying that the density or the likelihood of the image, say X, is just the multiplication of the probability of the ith pixel value given all the previous values. So what's going to happen is going from index is equal to 1 to the final pixel in the image, you will be generating the new image or the next image given all the previous pixels. So you take generate pixel number 1, and then you generate pixel 2 based on the previous pixel. So from this previous pixel, you will generate the next one. And then here you will have, like, what is it called? Pixel number 3 will be generated from pixel number 2 and pixel number 1. And then so on and so forth, so on and so forth. And this is how you represent a, let's say, image distribution, right? So it's a very difficult concept, as we said, to represent and to understand even, but it's something that is being represented in here as just the multiplication of the sequential learning of the pixels, right? Or the sequential probabilities of the pixels. So this is the probability of pixel I given x1 till xi plus minus I. This means that xi is being, learned or being sampled while all of these pixels are fixed. You already know x1 on all the previous pixels because you've already generated them or you've already sampled them. So this is just a technique that simplifies basically the understanding of the probability distribution of an image, right? So this is a very complicated distribution over pixel values, and you can easily represent it using a neural network. So the goal in here is to basically define basically the ordering of previous pixels. Do you go like this? Or do you go something like this? You see? So what is the order of visiting the pixels? Because pixels are two-dimensional, or images are two-dimensional, whereas sequences are one-dimensional. So you're going to have to find or figure out a way to represent the order or the sequence of these images. But pretty simply, or how they do it is, they will generate an image pixels starting from the corner, top left corner, and dependency of previous pixels will be modeled using RNNs or an LSTM. For now, the goal is just to give you guys just an introduction to what RNNs are or what LSTMs are, and then we will see them hopefully in the next lecture, I guess. Yeah, we'll see them, I guess, in the next lecture, where we will speak about RNNs in more depth, and we will see LSTMs, and hopefully we will also speak about attention models and transformers, sorry. So as you can see in here, it is not only generating this pixel as the next one, but also this pixel. So the dependency on the previous pixels is not like this, is not always like this, but now it's moving in two directions. This is just a simple trick that improves a little bit the results of the model, right? So you can define the order however you want, but this way allows the model to basically learn a bit better, because, for example, when you get to this point, you should not make predictions for this point given this point. You should be making it through these two. These are the most, like, these are the ones that give you understanding of where you were inside the image. And here, this is a very simple just representation, just tells you how it is being created, right? So either you do it like this, or you do it, you know, like this, or you could do it like this. Depends on how you want to order your sequence. The problem is sequential generation is pretty slow. What they decided to do is use CNNs instead of RNNs. So the simple change in here between pixel RNN and pixel CNN is they no longer represent the image as a sequential learning task, but they want to represent it, or they want to learn it through a CNN. We will see, as we said, next week what RNNs do and how they actually learn. RNNs are very sequential, and you cannot make any prediction on this one until you made the predictions on all of them, whereas CNNs can be, how to say, distributed or like parallelized, that's the word for it. So you can use the GPU and leverage all the cores of the GPU to make the processing much faster. So you're still generating the pixel or the image pixels starting from the corner, and the dependency now on the previous pixels is now modeled using a CNN over the context region. So here, for example, this is the pixel that you're trying to generate. And what you will take is all of the context before it that was previously generated before it. And that's the context that you will be taking as input to your CNN and generate a pixel output. So here you're trying to maximize the likelihood of over the training images. The likelihood is again the same. It's P of xi given all of these, but now it's not really going from all the way from the center or from like the top left. It's only about the context or the region surrounding the pixel you're trying to predict. So the goal is the generation is still slow, sequential, but learning is 100 times faster. So the training part is fast, but the inference part is still slow. Whereas for RNNs, pixel RNNs, both the training and the generation are extremely slow. So with CNNs, you can easily just, you know, parallelize, as we said, all of this, mainly because you have all the pixels at the training time, but at the inference time, you're still generating basically all of these pixels, so we can't make the predictions here yet. This is the only problem that they are facing here. And then the generated samples are actually not super bad. As you can see, it's it's a little bit blurry, and it's only able to do things for like 32 by 32 images. So it's not the best model out there. It's not the state of the art, but it is something that is worth at least recognizing or knowing that it exists, or it was like something that was, the state of the art in 2016, right before GANs came out and became the state of the art. So this is something that is also very much worth recognizing or learning about. The pros is that it can explicitly compute the likelihood of P of X, which is something that the majority of the models that we will be seeing in the future do not do. So models like GANs, for example, these are models that are not going to explicitly model or represent in any way, shape, or form the concept of P of X. So all of those models would just say P of X is too complicated. We're not going to even try to model it. Explicit likelihood of training data gives good evaluation metrics. So this is something that you could easily evaluate how good it is, but sadly, it's very bad. And it does give some acceptable results, but they're not good enough. The problem is sequential generation is extremely slow. So as you can imagine, you have an HD pixel, HD image of like 1000 by 1000. It's going to take you like, I don't know, let's say one CNN pass is 0.1 second times 1000 by 1000. It's going to get you like an hour to generate a good full HD image. Improving its performance, you could use, instead of just RNNs, you could use gated convolutional layers, which are similar to like combination of RNNs and CNNs, but they don't really help. So all of these training tricks and techniques, they really are not going to improve the results that drastically. It is important to note that you can do something called conditional image generation. And in this time, you're not going to be just taking the P of X, or you're not going to be taking just the pixels or the data, you're also going to take a class or a category. So depending on how you want to think about it, now we are in the realm of, are we actually in supervised learning, or are we still in unsupervised learning? So here you are in the realm where things are a little bit blurry between concept of supervised learning and unsupervised learning. If you define supervised learning as just any model that takes data and categories, that is a supervised learning model, then yes, this is a supervised learning technique. But if you define it as a model whose purpose is to predict the label, then no, we are still in unsupervised learning, right? So it's up to you, how do you actually define the concept of supervised versus unsupervised learning? So as we said, this is a little bit, a vague gray area between the two realms, because it does use the labels, but it does not use them in the way that you think it is. So the purpose is not to predict the label, the purpose is to generate an image. So it's still a generative model. So technically, even though it uses the label, technically, among us in this course, we will consider it an unsupervised learning technique. So I said, even though it does use the label, for us, we will technically consider it as an unsupervised learning technique, as the concept of supervised learning kind of is defined through this. You take the data and you predict the label. Whereas in this case, the label itself is kind of part of the data. It's not something that we're trying to predict. It's something that we're trying to use as a data point, right? So it's not really a label. It's just an extra part of the data. And here you're able to generate, images that are based on a certain class. So if you want to generate images for a specific category, you can just say, I want to generate the images, and you just put the category ID in this point, and it will generate some image for that category. Variational autoencoders, I'm not going to define them, but it's pretty nice if you guys want to look at the math behind it. So you could just continue looking at these slides, and it will explain to you concepts like the prior of Z. How can you use it how can you estimate it using the Gaussian? Conditional P of X given Z is a complex distribution. This is what we will be representing through the decoder, right? So given Z, it means the input is Z, and you're trying to predict X. So this is your decoder. You're trying to predict X given Z, or estimate this one, estimate this this model through a neural network. And that estimation, we will start calling it as Q. Let me go down a little bit. It should have it somewhere. No, it's not somewhere. Somewhere, Q. Somewhere, no, still not there. Yeah, so the solution is to basically, build a model that kind of estimates it through another function, which is the inverse of it, which is the defined or based on the encoder network that is trying to estimate the Q of Z given X. So this is what your model is trying to do, right? So given X means that X is the input, and this is the output of the model. So you're trying to take X and give Z as an output. This is your encoder, and it's kind of an approximation of the probability distribution of Z given X. This is something that you will never actually be able to calculate, but it just does not really exist, kind of. And this is where we go down a little bit to the math. So the Bayes rule, you simplify, 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 and you arrive at this function. As we said, KL divergence, you either have surely taken it before or you will take it in a future course. And this is basically just reconstruction loss, direct. And this is the part that we cannot really calculate. As we said, the probability of Z given X is quite intraceable in reality. So we cannot really compute this KL divergence term, but we know that the loss or KL divergence loss or the KL divergence distance, however you want to call it, it's always bigger than 0 because again, it's a loss or a distance kind of, and it is always bigger than 0. So what we will be doing is if we want to kind of reduce this error, we can just reduce these two terms, and this one will always be a positive number. So we kind of are trying to reduce, think of it as this scale. We're trying to get P of X to go down, and P of X is basically the sum of this constant, let's say this constant that is positive, plus this part which we can manipulate. So what we end up doing is we reduce this part, and it ends up reducing the total PX. So we just try to make this as small as possible, and that leads to a reduction in the total PX. And that's how basically variational autoencoders are trying to train. Again, you will see more about this hopefully in the future courses. But even if you don't, at least you have something to start with. So that's it for autoencoders and pixel CNNs and pixel RNNs, which are, as we said, explicit density modelers, generative models, whereas the GANs, which are the models that we're going to speak about right now, are implicit generative models, right? So they're trying to generate models in an implicit way without representing the probability distribution of the images or the data. So the problem is we want to sample from complex, high-dimensional training distribution. This is something that is extremely hard to represent. Even those who represent it explicitly, they try to represent it through like a trick, basically saying that the probability distribution of the individual images is just the joint or the multiplication of individual pixels based on the previous pixels, right? So it's going to be a multiplication of the probability distribution of each individual pixel in the image, which is not really how things are done, right? So it kind of takes away the concept of like not sequence, but like context inside the image, right? Just this idea that the pixel in here is not dependent on the pixel in here. It's just the other way around. Not very perfect. This is why it does not give good results. And that's why the trick or the problem of GANs that they're trying to do is they want to sample from a complex high-dimensional training distribution, but there is no direct way to do this. Even the explicit way, or the people who are trying to do it this explicitly, they're just trying to use a trick to get it done explicitly. They're not actually doing it explicitly. The solution is to sample from a normal distribution. So you just take a sample from a normal distribution. For example, by randomness, we sample this point. We sample from this point randomly, and then we map it or we transform it into an image. So you go from you build basically a model that goes from a Gaussian distribution into a distribution of images. We don't know how to represent it, but what we can do is sample from this distribution, and that gives us a vector, random vector, and then we convert the random vector into an image using a decoder, right? So using a decoder, you can go from a vector into an image. So what the idea of this was, you will be sampling from a random distribution and converting it through a decoder into an image, and that's kind of sampling an image from an image distribution. So instead of sampling an image, what we're doing is we're sampling a random vector and converting it into an image. That's the solution that the GAN has proposed for the problem of generating images. The question is, what can we use to represent complex transformation functions? Solution is always neural networks. So the idea is here, you take some random noise. This is something that you can easily do in Python, right? So random.rand, and it gives you your random noise, just a random vector. It just samples from the random distribution or the normal distribution. And then you put it through a generator network or a decoder. So the generator network is in reality just a decoder. It's just being called a generator in this case because it's used as a generator. But in reality, the layers inside are the same layers that you have seen in decoders before. So you have convolutions and upsampling. That's it. Nothing major, nothing complicated. The generator network is just a basic model that takes a latent space or takes a vector and converts it into an image. I just noticed that we are getting too late. So we're not going to be able to finish this lecture today. Probably the next week, we're going to just like go through it really quickly and finish it. The GANs, as we said, are very simple concepts. So maybe next week we will take like just 15 minutes from the next lecture and finish how GANs work. Okay?
Okay.
If you have any questions, please feel free to send them to me, and I will be posting the homework and the request for the project mid evaluation for the next week. So please prepare for that.
Thank you for the lecture.
Thank you so much.